Do we have any idea if people are connected online?
Yes, we have an idea, but now nobody is there. Usually we consist with online, but now maybe someone will join. It's also probable.
For example, Amnon or somebody.
Yeah, someone usually is. That's erroneous.
Is the population number when click. Exchange 3. I found.
So you might find some indices. So change of things like this was when equation had from August 2003 I was not able to write equations. So I can take a picture of the equation from my paper. So some bases are interchangeable here. Don't jump on that.
We are waiting for Sergey and we will start.
Okay, he should.
Yeah?
He just wants to play.
Yes. Coffee machine usually.
Yes, I think the coffee machine needs to be cleaned.
Well, since we don't have people on the connect to the internet, it's on us when to start.
So good afternoon, PCS members and friends. Today we have a scientific seminar and Professor Schechter will introduce our speaker and his topic.
Good afternoon. It's my great pleasure to introduce Professor Danko Radić, whom I know more than 15 years, and we are collaborating during this period with him. So his scientific career was developed in my eyes, so to speak. He was graduated in 1997, and then he got his PhD in 2006 on the subject of spin and charge density wave in quasi-one-dimensional crystals. Then he came to Sweden, to our group, and we start to work completely different things in nanomechanics of magnetic systems. Very fruitful, published to PRL during this period in Sweden. And he continues his research in our ISG groups here in Korea, working on nanomechanics. And today, his presentation will be his latest activity, which was focused on coherent and quantum nanomechanics in superconducting systems. So please.
Robert, thank you very much. It's indeed been my privilege and honor to come so many times and work in this inspiring and nice place since 2017, I think, to its last days. And in this particular topic related with CAT states and this coherent superconducting dynamics, a number of people were involved. You know our Korean friends, Tang Jun, Hee Chul, Junho, Robert and Lonya are already practically citizens here in Korea, and Sergey Kulinich, who I know from since my postdoc, in Sweden. He has not been visiting this place. He's in Ukraine working under exciting, at least, conditions, and I think he should be awarded with a medal of, well, courage or something like that. So this particular topic done in this SG group is related, as I said, with the cat states superconducting systems. And there is also, I draw attention, a dedicated each special issue of Symmetry Journal to these topics of nanomechanics and symmetry and quantum signal processing, theory and application. And the call is open since the end of February next year. So if anybody feels like, I invite you to submit your papers there. So quantum technologies, you will hear that term everywhere, and it appears in abstracts of scientific research paper, grant applications, newspapers, everywhere. What I consider quantum technologies are commercial technologies, something you can sell and get money for that. People are using that, which are based on quantum tools, such as quantum superposition, entanglement, topology of wave functions. So in the sense of quantum signal processing, in the field of quantum sensing and metrology, it would be, of course, example, SQUID, quantum motion sensors and accelerometers based on quantum interference, and then devices used to measure electron charge with high precision based on quantum Hall effect and topology of the wave function. In the field of quantum computation, so far it is only the quantum computers based on Josephson junctions by IBM and trapped ions done by some other companies. In quantum communication, we have only so far quantum key distribution platforms used for cryptography in classic satellite communications. So I will not talk about that. What I will talk about is physics, as physics is our sometimes lame, sometimes.
The previous slide, the last picture, doesn't happen. Last experiment.
Can you say louder? Would you proceed?
So there's a proposal to do this distribution of a satellite, but it doesn't happen.
Wasn't too bad.
It did not happen. It did not happen because of the disagreement between two groups.
Yes, but those are really modules. So these QKD modules which are used for quantum. So okay, they maybe still not realize that, but I've heard people are using that in institutions to establish cryptography in their networks inside the institution. So this might not be okay. Thank you. That might not happen yet. Okay, so this is our physics, our attempt to improve this technology by fundamental research. So in the direction of this quantum signal processing, the smallest unit which you need is something that preserves phase, and that would be like two-level system, and so this relative phase is there in the superposition of two levels. So in the direction of optical qubits, which is a rather well-developed research, this is so-called cavity QED systems. It is on the verge of commercial use. Maybe not, but it is close to it. These are systems based on photon-matter coupling, photonic coherent states, light polarization states. It's rather well developed. And the other, still not technology, but research is related to nanoelectromechanical systems. And these are systems based on optomechanical coupling, electro and magnetomechanical coupling. This research and direction towards technology is still, well, we can safely say, in its diapers. So it seems really matter of fundamental research still. Now, why one could wonder why bothering nanomechanics? So it is potential reward in terms of huge quality factors achievable today, depending on system, of course. Rather small form factor, orders of magnitude smaller comparing to optical systems. Unfortunately, you need to go to millikelvin oscillation temperatures, and this is the disadvantage. Now, there are, of course, other systems, some spin chains in which, well, I get a bit disappointed because usually people have well-developed numerics to calculate spin chains and then just change the word spin for word transmon and proceed further, but I haven't seen realization or a proposal of physical realization of such systems. Recently, I've heard of graphene and valid pseudospin combined with real spin of electrons used to realize qubits with, I think, the coherence time quite long, of the order of dozens of seconds, something like that. So I just recently heard about that. However, I will focus this presentation on nanoelectromechanical systems. So let us.
Can I ask you, how is this? You go back one slide. So how are these numbers you presented, the quality factor and the form factor? How is that compared to superconducting devices?
In what sense?
Well, Josephson junctions also have quality factors.
Yes,
for qubits and so on. I mean,
I will come to that. Yes, that's.
Can you just comment? I mean, are these comparable, these quality factors, or
Charge qubits, its decoherence time is, I think, today 1 microsecond, up to 1 microsecond. So it is the bottleneck of your device. So our aim is to use this charged qubit, the ease of electrical manipulation, and then transduce the quantum signal into nanomechanics, which has quite high quality factor, orders of magnitude higher than charged qubits.
So what is the quality factor for these charged qubits, roughly?
The coherence time 10 to 2, for example, something like that. Is it? I didn't calculate. Rather small compared.
It's a tunnel with the levels in the dot.
Yeah, but I'm just asking, since we see numbers here, so what are the numbers there, just to get a feeling?
But I know is that if you make a atomic junction with the superconductor, then the quality factor is around 10 to the 4.
I thought, yeah, it's actually even more.
And if you make a Josephson junction with the nanowire, then the quality factor increased up to 10 to the 6.
And the temperatures are similar.
Temperature very low,
Around
10, 20 millikelvin.
Millikelvin, like.
Yeah.
But charged qubit is then the weak link, because charged qubit is a grain which is susceptible to all noise, electromagnetic noise around, and it becomes the weakest link. Whether you have good quality factors, nanomechanics, Josephson junction, or whatever, but this grain then becomes.
There was a Josephson junction used for making qubits in reality. So they work in devices.
Yeah,
already. It's not a fantasy.
I ask you, but this is 10 to the 9. It's already achieved.
It is with special membranes, so 2-dimensional membranes, diamond or something like that. I found it. Okay. So this is the schematic proposal of the device we will consider in this presentation. It is so-called AC Josephson setup, in which we have 2 superconductors biased by bias voltage, and between them is this infamous superconducting grain of mesoscopic size. It is attached to nanomechanical oscillator, So you can vibrate in principle in 2 dimensions, plane in x and y direction, and so that the tunneling amplitudes for tunneling of Hilbert pairs are position dependent. There is also gate voltage, which serves to manipulate the states inside this superconducting grain in a desired way. I will show how we do that. So just shortly, what makes the superconducting grain a qubit? If you have superconducting grain with n electrons, expose it to gate voltage, the electrostatic energy of this system due to finite capacitance can be manipulated by the gate voltage, and in the way to bring the energy of the system with 2n electrons, so n Hilbert pairs, and energy of 1 excess Hilbert pair degenerate, while the states with odd number of electrons will be scared away by the superconducting gap. So this degeneracy then has a wave function, which is there. You show their linear combination, and this is what constitutes our Hilbert pair box or our charge qubit. Hamiltonian of the system comprises Hamiltonian of the leads characterized by the phase. Then this is the Hamiltonian of the gate electrode, Hamiltonian of the harmonic oscillator, in principle vibrating in 2 directions, and finally the tunneling Hamiltonian, which performs the careful bookkeeping of tunneling of 1 by 1 Hilbert pair between this grain and the leads.
Sorry again to understand. So these 2 states with n and n plus 1 Hilbert pairs, these are the numbers of the Hilbert pairs on one of these islands, or one on the left and one on the right?
And n plus 1, this is here.
On this yes, on the central, on the island, on the shuttle.
Yeah. Yes, shuttle.
Which
we can call it in some sense a shuttle. Yes. Okay, so we express the Hamiltonian, combine the terms in the following way. So the qubit base is characterized by these Pauli operators. This is the qubit part. I will explain it to the Hamiltonian. This coupling part, this is the charging energy on top of the once created qubit. So additional effect of electric field. We will use it later. And this is the harmonic oscillator. Here at this stage, we choose to treat only one-dimensional harmonic oscillator. So the superconductor phase, it is simply different between the phases of bulk superconductors. So they define Josephson frequency. This is the bias voltage, and the phase linearly grows in time. And then this form is achieved by expanding the tunneling amplitudes in terms of small parameter, which is the ratio of 0-point motion amplitude. This is of the order of picometer, and tunneling length is like angstrom. So it's small parameter, and combining these terms, we get that this term here is simply Josephson energy. The coupling is characterized by small parameter, and it is linear in mechanical shift coordinate operator, and we choose a case in which there will be no additional electrostatic effect except of creating the Hilbert pair box. So that would be our starting Hamiltonian at this stage. This is the qubit part of the Hamiltonian, coupling, and one-dimensional harmonic oscillator.
Sorry, the question, this the Hamiltonian, is the sigma z term. I think I understand the first term proportional to the cosine phi, because normally the weak link is the coupling, Josephson coupling proportional to the cosine phi, but here the sine phi, how did you get this term?
This one?
Yes.
It comes from these terms. You see, these terms here.
Distance.
When you work on this Hamiltonian and combine all these terms, we will get one symmetric combination, or this anti-symmetric combination with minus sine phi. And regarding this, Pauli operators, it depends on the basis we should choose. You can choose charge basis, Josephson basis, even current basis. I'm not sure how to construct, but this
So
is in principle.
if there's no vibration, then this term is zero.
This one,
If you place the shuttle in the middle and let it not move, then this term will be zero.
in principle, yes, there is no.
Because you have full
It is coupled to shift it is linear in shift in your coordinate. It would be zero in the middle.
Extra term because we have not two bodies superconducting, but three bodies. We have superconducting leads and we have in between superconducting gray. So it's more complicated than for standard Josephson junction.
Yes, I did assume the symmetry of the junction. It would be more complicated without that such.
So does this Hamiltonian, do you need to do perturbation theory?
As I said, I got my answer to some. It's not perturbation theory. Simply take this Hamiltonian and combine the terms, you will get this. I mean, this is technical. This is technical detail. I can show you maybe out of the same.
Is there some phase on island?
This is small object with discrete states. We do not assume it's undergoing that. So we say we know this is n and n plus 1 electrons. So because we are tunneling one by one effect.
You want to say charge is a good quantum number of something.
In the
shuttle.
gray. Yes.
So it's not commuting. George energy and Josephson energy.
Well, again, the charge on the shuttle is a well-defined quantum number. You distinguish between n and n plus
Yes.
1 after all
Yes.
this, right?
Yes.
But if it's resonant, in resonance, they talk.
Well, it's a different story. It's resonant.
So there is no.
But what is y? The coordinates y. Yeah.
It is coordinates.
Yeah. What
X and Y are coordinates. What is it on the?
This is shuttling in the orthogonal
Okay.
direct.
But
I
this
see.
is X and this is.
I see. And is it important or you disregard it?
At this moment, it is not, but further on it will be.
Right.
By the end of the presentation, it will become.
You saw the previous slide when we had the full.
This is not the full
previous-
I told you, I choose the case to treat only the one dimensional.
Danko, the previous slide, he's asking for the previous slide. Right, okay.
So here I assume the possibility of vibrations in y direction.
And then how do you like integrate out the lead? Yeah, how you integrate out the lead? How you do it only on box?
So
The Hamiltonian is the next slide, only on the box, right? Right, the sigma is only on the box, right?
on the
Box or
Yeah,
tunnels, whatever you call
what
it,
about?
is the question.
What is the question?
So the question is how you integrate out the lead to have the Hamiltonian into box only.
I mean, you have several Hamiltonians on the previous one, and he wants
You
to
mean
know why
this
they are-
large Hamiltonian?
Yes.
Well, this is now this summation over n will give you the definition of the phase, and that is by what this
Mhm.
this.
So you treat tunneling perturbatively. So in the zero
Right.
tunneling approximation, you have standard superconductors,
Right.
which we know how described.
Right.
And we have standard dot.
Right.
On top of this standard picture, we have tunneling as a perturbation.
Right.
And we get extra term in Hamilton.
Right. So I think that you get from the perturbation theory, not like exact. The next Hamiltonian is perturbation.
In tunneling.
Right.
But of course, It's a proof.
It's not
You
particularly.
don't have weak superconductivity, you don't have Josephson effect if tunnel is strong. Then it's homogeneous superconductor, supercurrent flow, and no Josephson effect at all.
So for
So you have to consider it.
this Hamiltonian with assumption that the tunneling is small.
Yeah, small tunnel. It's new physics come from the weakness of this tunnel.
So numerical solution, I'll just short elaborate. This is what some Joule and Joule did, which was the basis for phonon parts, and then these two components. Basis for qubit part, the time evolution operator was calculated in more or less standard way in numerics, using initial state to be the ground state both of the qubit and harmonic oscillator. Wave function is then constructed standard way using some parity properties or symmetries on starting Hamiltonian to help to get some relation between coefficients. And the result is then divided in two classes. So the first class is resonant case between mechanical and Josephson frequency. And you see that distribution of these coefficients characterizing the wave function. So over states and over time depends like t squared. It's like parabola. And then you get in non-resonant case, I would say slightly non-resonant case, so this is just 1%, it immediately you get this periodic pattern of coefficient intensity distribution. So when we analyze this, we got that these states, these results, states we get, are actually the eigenstates of mechanical annihilation operator, which is known as coherent states.
So
And
again,
this-
what is I'm lost somehow. So you plot here the number of periods, so basically like time, yeah?
This is the time, yes.
Time,
number
you
of
could say
periods.
time, yeah?
It is time.
And n is little n is again what?
It is the Fock basis, and population. This intensity is the population of certain state.
So you have some in this resonant case you probably, which is expected maybe, but what you show here is some kind of non-stationary state, yeah? So I mean, you pump the system up, I mean, so this probably should stop or explode or do something like
Yes,
that.
it should explode unless there is there is physics around it. It would not explode because it would, before that it would go to some dissipation regime, nonlinearity, whatever, that you cannot construct coherent state anymore.
Okay.
So ideally it would explode. Okay, so this case corresponds to, let's call it the analogon of classically driven oscillator in resonance with driving with amplitude which grows linearly in time. Well, this case would correspond to classical beats. When you're slightly off resonance, you get this beating behavior. So if you project this solution to classical phase space, you get this initial condition, you start to develop this linear in time trajectory, growing in time trajectory, and these features come from some complex dynamics between oscillator and qubit that we have. In order to understand this result, we of course obtain analytical solution using standard interaction picture within the rotating wave approximation in resonant case. And it turned out that we managed to get analytical solution in terms of Bessel functions. So let us focus to this evolution operator. What it has here for the case of simplest resonance, so omega is equal to Josephson frequency, mechanical frequency, Josephson frequency. What it has is, so this is the qubit operator, and this is mechanical momentum operator, which in this combination exponential function defines the coordinate shift operator. So indeed, what it does is to create two coherent states, one of them shifting in one direction, the other in opposite direction, and this shift is given by time, and time number of periods, time. small parameter, and this is now something of the order of 1, like this is the characteristic scale. So n times x0 is the shift of these coherent states, one in one direction, the other in another direction, and these two coherent states are entangled with states of the charge field. So we get entangled state between nanomechanics and charge field.
Danko, sorry, can you show previous slide? Just some naive questions. So if you in resonance, if I have classical anatomy, you have shuttle instability. Yeah, you pump
It's
the
not,
energy.
it's not instability, this is pumping. It is like instability is when you have system, for example, exposed to constant voltage, but due to some internal mechanism of, for example, negative differential conductance, you get that you get negative dissipation. This is instability, and this is driving, some sort of driving, but not very obvious. So this is due to entangling nanomechanical state with Cooper pair box state, and then passing with just the Cooper pairs between.
Well, again, little n is small n is the state of the vibration.
So Fock state, yes, index of the Fock state of the harmonicals.
of the vibrations of nanomechanical.
Yes, yes, yes.
So I mean, if n grows, your amplitude grows. So you do have instability. I don't know why we say no.
Well, is the
Pumping by external source.
It is probably, but what did Anton say?
would you call instability if you have pendulum without friction and you expose it to external periodic force in resonance with mechanical
Yes,
forces?
it's
Is it instability? In that sense, then it
Okay.
is. I didn't call it instability. We call it driving.
We call instability negative.
So it's unstable. I mean, it just goes to infinity.
If you
That's-
go
that's what
from
it's
quantum distribution to classical, yeah.
What is unstable?
This your thing is unstable. I mean, n grows.
Why? Because we do periodic.
Because you drive it in resonance. That's why things go unstable.
Okay, it's a more wide definition.
It's a very
Okay.
There are two possibilities. Either you modify friction and make it negative. This is what we call instability. Or you have fork of external force, which in resonance is your.
I mean, this is this is standard. Why this is standard instability, for instance, called Mathieu instability or Hill's instability. If you take parametric driving, you get unstable. Is this growing exponentially in time?
No, this is linear in time. Linear.
Well, it doesn't look linear.
We'll break down before I
We
go.
call it.
But it doesn't look linear to me. It looks like quadratic or.
No. This is distribution of coefficients in the state. So you
Yeah, but n grows on average somehow, and it doesn't grow linearly in time.
it goes quadratically in time, but when you put this n in this thing here, you get a linear in time growth of amplitude. It is analogous. So is it somewhere? No, I didn't write it here.
It's parametric driving. It's parametric driving, right? And you have an instability to the parametric driving. Why do we discuss the? I just try to understand.
It's not
What is
parametric
this in-
drive.
Huh?
It's not parametric.
It's not.
Yes, it's direct drive.
It's what?
External field.
It's additional. It's like an external force.
External
We work on it.
So what are usual classical instabilities? For example, you know what is van der Pol oscillator. Van der Pol oscillator, it has term with negative friction without external driving, and it gets unstable. You get something like this in phase space. That is what I call unstable system. So this is okay. I think we are now on philology. Okay, now that we are having the parts from which we can make something, let us make some cats from this. So the creation of cat states is now the matter of protocol of operating our device. So let us first consider this type of protocol. We switch on bias voltage, and during n periods of time, an evolution is driven by the operator that I just described, and the wave function is what I just described. Then we switch it off and have some rotation in phase space. There is no inflation of coherent states anymore, so it is just rotation. So each of these states gets some complex amplitude, which it is here. And then we switch on the bias voltage again for some number of periods. And then each of these two states split in two. So each of them, here they split and starts to get inflated again in opposite directions. And at the same time, they are entangled with qubit states. So this is now the solution after m periods of time using this problem. Okay. Now let's.
What limit now the dissipation in the mechanic path?
Yes. But I will come to it. I will come to this dissipation. So to visualize this solution, we construct the Wigner function of mechanical subsystem. It is this term here. It contains this W0. It is simply the Wigner function of coherent state. It is this nice Gaussian shape like a bell. It's never negative, and it makes this solution these combinations that you see here. So here we have this is the initial state. These are two coherent states. This in one direction, another direction. Then you switch the bias voltage and continue then after one period with applying bias voltage. So they split, and there appears this strange red and blue pattern. It is in fact the interference pattern, negative Wigner function. So this Wigner function has a negative part. It's not a miracle. I mean, any quantum system would have negative parts of Wigner function. It's the indication of quantum superposition. But here, these states are practically semi-classical. They are practically classical. So you bring it into superposition to semi-classical objects of opposite nature, one shifting in one and in opposite direction, and they interact. This is by definition called the Schrödinger cat state. So you have good cat, angry cat. This is my cat. Actually, I had this picture. Then we have in superposition, and although I'm a theoretician, I can confirm that this state is real. The scratches on my hand. Okay, now let us see what these effects you asked me about can bring. So first we examine this out of resonance effect. So this curve here will be the perfect resonance, this t-square law of distribution of phonons in the states of time. So this is mean number of phonons. And if you're off resonance, you see this blue line is 5%, then this would be 2%, this is 1%. You see, we can say that they are going with each other well for small times, and this time is longer. The deviation from perfect resonance is smaller. And here is what I just said. So this is why it is linear in time. If you have driving of monic oscillator, the amplitude was linear in time. If you have slight deviation from the resonance, you have these classical beats. And this is the simulation, how it looks, quantum mechanical simulation, how it looks and what effects it has, each of these deviations has on our cat states. See how it looks when you have, after long time, of course, we have these classical beats, it's simply oscillations around origin. So our aim is, of course, to get this for the practical use in these well separated coherent states to constitute good cat states in the sense of future quantum signal process.
Okay. The period of this oscillation is equal to quantum entity, and then
the period is 1 over
the period of this oscillation.
This T.
Yeah.
Okay. So it is defined by the mechanical frequency. So this is always period of mechanical frequency 2 pi over omega, and we are studying the deviation of Josephson frequency from the mechanical.
Yeah, but the oscillation of this small thing.
This period, I don't know. You see, there are beats. Beats are this. This is this defines the oscillation of the field. So, yeah, it is some. It depends it depends on your deviation from the common durability.
1 over delta O. 1 over delta O.
1 over delta O. Yes, delta O. I didn't hear the word delta. Sorry. Okay, so now this simulation is the deviation from the instant switch off and switch off in voltage. It was done by my student Mattia for his diploma work. All of this stuff, and really, I mean, you'll see. This is just to see how the cat states are affected by this, because it brings inside additional harmonics in your processing. So you need to be careful about that. And finally, your question about dissipation, about the coherence effects. For that, we use this Hilbert-Master equation, where the sources of decoherence is exactly the loss of phonon dissipation and random qubit state flip due to this electrostatic, electromagnetic, whatever noise from the surround. Well, it might look harmful, but this is actually the main culprit from the for the non-commercial, still non-commercial use of charge qubit.
I think like to be precise, I think that's the J loss here. The coefficient need to be focused on to the amplitude.
So this is how you treat it. This is so you treat this in this Hilbert equation. You treat the contribution, the operator, which contributes to something that can happen to your system. So you can lose the phonon from your coherent part.
But my point is that the gamma loss, you have two gamma.
Gamma is the rate.
Yeah, right. I think that the rate will be focused on to the amplitude of the N. How strong will you vibrate? So this basically will. It's defined by the quality factor. So it's not so much maybe amplitude, but it's more to the connection to the environment. If there is a nonlinear effect which is proportional to product of some function of amplitude and connection to environment, then I agree. But here we take it constant.
No, it's just endorsement relaxation time. So it's not for the village.
It's simple word.
Okay, so technically what you need to do is to deconstruct this system, put them in terms of pure ensembles, and then go through numerical solution. And what you see for this combined effect is that previously nice, so this is the resonant effect. So in resonance, previously nice T square law, distribution of coefficients, now gets washed out. So this is the without dissipation, without coherence of any kind. We see that the coherent states are not so well separated anymore, and there is this incoherent mixing between them. And this is how it affects the cat states, which you maybe remember from previous picture, nice and well separated. If you calculate negativity, this is the measure of entanglement. We see that although it rises up over time. So, but then it gets its maximum, and then due to the coherence, the entanglement starts to be lost in the system. So the main, as I said, the main culprit for this is the very short charge qubit lifetime. It is from Nakamura's 10 to minus 7 seconds to nowadays 10 to minus 6 seconds.
This is answer to your question.
And this is the bottleneck. This is the bottleneck for our system. So the idea is to use the ease, as I said, of electrical control and manipulation of charge degrees of freedom, encode the signal into charge qubit, and then transduce it to nanomechanics and do the further processing with it.
But is it dependent on temperature, gamma loss?
Gamma loss and
Gamma loss will be
it's the loss of phonon. Maybe if you increase the temperature, maybe you can absorb some.
Oh, but vice versa. I mean, you couple too many degrees of freedom, yeah, you have some, I don't know, average distribution function.
Yes, and then, but since we are already on the, since we are already on the 15 millikelvins, and at 1 gigahertz we work with much higher energies in millikelvins, then this low temperature will not be so affecting this system. Okay, before I go to this transduction of information, I'm just maybe show it 1-2 slides. I'm speaking about some science fiction, or experimentalists can actually do it. So Josephson tunneling, suspended single atom transistor, and then grain on nanowire. These things are experimentally achieved. Our friend Jules, collaborator Jules team, is working on these nanopillars using this CF4 plasma grinding techniques, then this electron beam lithography, ion etching of this. So I spoke to Jules team and John Kusuk. They said there is no physical obstacle for this effect. It is the matter of skill and art and will of the experimentalists to do it. I know it can be a lot. It can be. So this is the list of parameters. They are within reach. So 1 microsecond decoherence time for a charged qubit. We used moderate force these pillars and suspending nanowire quality factor, Josephson energy 0.11 Kelvin, tunneling length. This is angstrom. This is then mass should be the grain mass should be large enough to sustain superconductivity, but not too large to lower the frequencies. So this is actually okay for aluminum.
From this, we can see the Josephson quality factor of the same as mechanical, because frequency of our oscillations 10 to the 9 and relaxation time is 1 microsecond. So it's 3 or 4 orders of magnitude. It's the same as this Q.
Bias voltage is very important to be controlled precisely because it gives our resonance condition, and indeed it can be controlled by devices from several years ago to 0.1%. So at 1 gigahertz frequencies, or if we use higher vibration mode, 10 gigahertz, we can achieve this shift in coherent states up to 10 to 2, 10 to 3, 0-point oscillation.
What is a typical 0-point oscillation?
Pico.
Huh?
Pico.
So this is
0.1 to 1 nanometer.
1 nanometer.
Angstrom to nanometer. It would be the average. Okay, now finally the main topic of this talk. This was introduction. This is schematic picture of quantum signal processing unit. This is, we call it quantum network, comprising n terminals with superconductivity, superconductor leads, Cooper pair box, and gate electrodes attached to one single mechanical aspect. Why? Well, to spread entanglement, we will spread entanglement by nanomechanics. So each of these terminals has, as I said, Cooper pair box, it has superconducting drivers, and then strategically, symmetrically placed gate electrodes with this controlled additionally by this delta V in specific way to create zero additional potential in the middle of the junction, but electric field. So gradient it is 0 for x equals 0, and then electric field is gradient. So you can add electric field effects to the manipulation of the states in the Cooper pair box, while you don't disturb your well, the very Cooper pair box, the superposition of the general states, and you can do it while you are inside the superconducting size of the superconducting gate. So not too much. Okay, so the Hamiltonian is, as I said, single nanomechanical oscillator, then n qubits. All of them are coupled in their terminal, and this is this additional gate control. So this is the energy coming from this electric field, and it is also proportional to the linearly proportional to the displacement, to this x.
Sorry. So, in the beginning, you had coupling in x direction, yes, due to displacement, and the voltage was in y direction. Now you put
What voltage?
gate voltage. When
Yes,
you
okay.
so you had just sigma 3 and some
It is
gate
the
voltage.
function. It is the function of x and y. So voltage, it is a electricity. Energy is a scalar, so it's some function of x and y.
No, but here you have just oscillation in one dimension.
Yes.
And due to superconductivity, you have coupling via sigma 2 and phase, and also due to gate voltage here, which is last term.
Yes.
Sigma 3. Okay.
And what is small n?
Small
N.
Small n.
There's a spoon and
What is small n?
summation.
Sigma 1n is index n.
What is okay? It is the index. It is the index of the terminal. Of the terminal itself.
But that is also because different vibration mode and coupling differently, right?
Yes.
So basically,
Yes. You need to be careful about at which side it vibrates.
Right.
You are correct.
and then the coupling
On the next slide. On the next slide.
Okay.
On the next slide, you see the simple case with two terminals, and exactly what you said. This is what you were talking about. It's important.
But then now, if you consider the vibration as a coherent state, like previously,
We will build the coherent state.
then the coupling will really depend on the mode of the oscillation.
Yes. You see here, I will use that what you said.
Right? But it's complicated. Like at the end, if you have too many modes, it will be.
I know. I preserve.
Phenomenon. We can set voltage to each frequency separate.
Yes.
We can resonantly couple to third mode.
We can excite particular.
It's a resonant phenomenon.
So can you still use?
We can select which mode we would like to couple in the resonant by voltage, by bias voltage.
And then you will not use a coherent representation mode on the string anymore, right?
Coherent representation of.
We can use the same thing.
So
Coherent.
look, this we preserve. So it is only we excite the second mode and resonantly drive it. We don't mix it with third or the fundamental. Then everything would be lost. So okay, I think that this Hamiltonian is understandable. With one additional comment, I use one trick here, not trick, but approximation. So you see here, it's not shift operator anymore. It is now the amplitude of the coherent state. So you need to be careful to use that when coherent state is already well developed. You cannot use it at the beginning. So we will switch on this term when we have well developed compact coherent states. So here it's practically the mean field approximation. Yes, we calculated that exactly. The calculation is long, but brings no additional knowledge except details. So this is approximation we will use further on. In principle, we will use three types of time evolution operators. So the first one is only with bias voltage switched on. Gate voltage is additional, this delta is turned off. It is the evolution operator, which I have described. So this is for first, this is for second terminal, plus minus, and lambda is this shift proportional to small parameter, and I explained that. Then the second one is when we switch off all the voltages. We decouple the system, so we have in principle unitary rotation, and with the remaining phase, we have some coupling to qubit. We can kill this. We can kill this term by setting the phase to pi over 2, or 2 pi n plus pi over 2. And this is what we will use. So just to perform unitary rotation of the coherent states in the phase space. And then finally, this is just electrostatic evolution operator, so to say. We set bias voltage to 0 and delta V to finite value. We will use it over 1/2 of the period, so it rotates. And here you see this term here, this evolution of qubits affected by sigma z. So it will, well, so to say, rotate the qubit states, but the sign, the direction of this rotation, the helicity, say, would depend on the sign of the shift. So if you are in the positive half plane of mechanical shift, it will rotate in one direction. If you are in the opposite, it will rotate in the opposite direction. So clockwise and counterclockwise, so to say, rotation of the qubit state. Okay, this will also be used, and I will show it soon how. So let us now try to perform the basic task, signal processing task. Let us try to transfer the signal from between one qubit to second qubit in this quantum network. So what we will do is, as I said, to encode the quantum signal, these amplitudes, coefficients alpha and beta, into the qubit state. So it's a pure state. This is nanomechanics. Then we use our magic and create entangled state. And then further on, we want to transduce the whole quantum signal, so alpha and beta, into this linear combination, into this cat state. So this is the plan. We will do it in this network with two terminals, so it will be like this. Quantum information encoded in the first qubit. The second one is in the same state. Then we use forward protocol to create this state here, transduced completely to nanomechanics. And then with so-called backward protocol, we will, with now first two states are in the same, and the quantum information, this alpha and beta, is stored in the second qubit. So in this process, we have shown in a paper from 23 that the entanglement oscillates between entangled, fully entangled, and pure state. So the matter of performing this task is when you make not a read out, when you take the signal and do something with it, whether it will be you need pure state or maximum entangled state. So let us now.
But can you prepare the state, because it will evolve in time, right?
Yes. This is for Neumann entropy, so it's not a state. It is the measure of entanglement of this process. Now everything will be clear. So this is the code, the program of our device. This is the operational protocol of bias voltage at the first terminal, bias voltage on the second terminal, gate voltage, this delta V on the first terminal, and gate voltage on the second terminal. This is the resulting phase, first and on the second terminal. So this phase difference between superconductors. And let me now show what we do. So we start with the initial wave function, initial state, with alpha and beta stored in these two states. First qubit, so this is first qubit, this is second qubit. Now the second qubit is in the eigenstate of sigma x operator, so it doesn't affect them. This is the trickery we need to use in when we construct the protocols, when we program our device. So this is the first evolution operator during this first phase, when we switch on bias voltage and don't switch anything on the second qubit. So this is first, second terminal. So after that, we come to the state in which we have this entangled state of qubits. So second is unchanged, and we simply build up coherent states. It is shown in this picture. So we start from the middle of the phase space, and then pump up, inflate the coherent states to minus Z and Z, starting with this. So these states of qubit are not changed. Then we pick, so we put a pulse of V0 on both terminals in order to shift the phase by pi over 2 with respect to some integer 2 by n. So what it does, it kills this cosine term appearing, which would affect which would produce some qubit dynamics. So we kill that part and we simply perform the unitary rotation into phase space. So during this quarter of period, here and here, we bring these states into strategic position. We simply add phase to the mechanical states. It is now this resulting wave function. Then we evolve, so now we are here. Then we switch on so the bias voltage is switched off all the time, so there is no coupling, it's just manipulation with qubits. We don't inflate the nanomechanics. Now we switch on the gate voltage during 1/2 of the period. So it is this phase here, this stage 3 here. So what we do by that is, in principle, since this coherent state evolves along the negative part of x coordinate, and this one along the positive one, they will rotate the qubit states in the opposite direction. And what we want to get is, you see now, after this, the first qubit is in the same state, while the second qubit is in what the first one was in the beginning. So, and both of them are carrying, as you see, both of them are carrying this quantum signal alpha and beta. So this first qubit is now in the EX, both of them are the same, while the second qubit is now in the opposite state. And then finally, we bring them to, again, strategic position, which we need in the phase space by this part during the quarter of period, analogously to this and this stage of practical descent. And finally, in the last stage, we deflate the coherent states by, as I said, batch protocol, so opposite sign. We, so to say, pump out the coherent state, and we end up with a wave function in which, from previous qubit, from first qubit, now the quantum information, quantum signal alpha and beta is being transferred in the second qubit, and we end up in this. So this is example of how the operation of quantum electrodes transferring quantum signal between two units can be performed. So having this task accomplished, we were thinking about, okay, fine, can we connect the parts of the net in some way? So idea was to design, so to say, quantum trajectory in 2 dimensions. I know it sounds oxymoron because quantum trajectory, because the uncertainty relation is not comparable term, but not so horribly because coherent states are already in the states classical, as a classical with minimal uncertainty, but there is additional thing, there is a superposition part. So this, what I call quantum trajectory, would be something moving of coherent states, preserving this quantum coherence between them. And in order to do that, we underwent the task to create 2-dimensional cat states. And this is the suggested device. So again, this is now a pillar with a superconducting ring, Cooper pair box at the top, superconductors, the same philosophy as before, schematically gate voltages with now here additional gate voltage, which can in principle be the AC signal. And I will show why we need that AC signal. So this is standard Hamiltonian H0. Now we consider vibrations both in X and Y directions. This is important, 2-dimensionality of future cat states. And this is interaction Hamiltonian. So by EX, this is this Josephson coupling, which I described. And by epsilon y, it is the part containing electric field and containing the signal applied to gate electrodes, which can oscillate in time. We tried with constant signal here, with signal with 1 omega t. It produced in the time evolution operator at both of these positions produced minus. So it means this would be mechanical shift momentum operator, this would be mechanical. So it would just shift in x and y direction. You will have some linear motion under certain angle. But this combination here gives you here minus, so it is momentum, and this is the shift operator. It is the entry point to Lissajous, so to say, motion in the xy plane. So yes, okay, now you get this entanglement with this qubit and x coherent state, x direction, y direction, as they are harmonic oscillator, they are not independent, but except of this entanglement which you achieve by this complex dynamics. And to put a long story short, when you integrate out momenta, you get indeed in 2 dimensions, you get this circular or elliptical quantum trajectory, which you see has here summation. So it has superposition of these 2 states rotating like this. And this trajectory preserves quantum trajectory. The system preserves quantum coherence. Now the question is what to do with it. So this is the last slide suggesting this device, and if you use simply a constant signal on the gate electrodes, you can imagine to develop this quantum trajectory between parts of the terminal quantum terminal 1, entangle it, and then develop it and spread this entanglement in this between the parts of another quantum terminal where this angle is controlled by ratio of electric field and Josephson energy. And it's a simple function representation of this result, not to go much longer. So the future research, just a few words. At this moment, it is related to how to avoid the quite requiring and demanding needs of resonant pumping. We have some ideas to use simply a mechanical heat and produce the coherent state at once, like pulse or something like that, and then see its development. In the phase space, we have preliminary results which are positive. And the second task would be to realize the basic elementary unit of some quantum processing chip. It is the C0 gate in which qubit and control qubits, I'm sure which one is which, depending on control qubits, the target qubit is, if control is 0, it's unchanged. If it is 1, it is switched. So we also have some ideas how to achieve that, but this is the matter of our future activity. And finally, I will conclude. I've shown this design of the gate states using quantum tools, transduction, entanglement, so how to process quantum signal. As I said, it's difficult experimentally, but fundamentally not impossible. So me and my cat, thank you for your attention.
That was quite long, sorry about this. But questions, please, if you have, there was a lot of questions.
Or what is advantage over this over the usual like superconducting qubit? What is the advantage of that?
The advantage of this over IBM's system. So far, there is no. This is in diapers. This is in diapers. IBM is already a commercial device. I don't see, honestly, I don't see that we will exchange this multi-qubit network with thousands of entangled qubits that they do, but maybe some critical parts which require very small form factors could be related, and quantum signal can be transferred or processed by using of nanomechanics.
No?
A bit stupid question. Personally, I hate such questions. It's about experiments. So I've seen from Joe Keys and John Post's work that this device exists, so to say. How do they cool the system to have Cooper pair box? With liquid helium or?
It's both. Okay, so it is sort of passive cooling with liquid helium, then you can have negative pumping, so pumping out of vibrations to put it to the ground state, to put mechanics to the ground state.
But in their device, I thought they
You need to
drive
couple them.
and deliver.
I don't know. That is a different thing. Okay, that is, but in principle, you need to have coupling and you need to do opposite to what I'm doing. So you have a coherent path.
So pulling via nanomechanical things, yeah.
Through coupling to pulling of nanomechanics through coupling to electronic system.
If there is no more question, just think again